Hi everyone, welcome back to my channel. So right now, imagine that we are working in a supermarket. Maybe we're a manager there or a marketing staff there. This supermarket sells more than 800 products, and we've recorded the volume of sales for these products every week for the past year. And now we want to see the similarities among these groups in terms of sales trend. I don't know, maybe we might want to make different marketing plans for each group, or we might want to make forecastings. It's going to be a lot easier to make one model for each group rather than making one forecasting model for each product. So more formally, we're going to do time series clustering. More concretely, we're going to study HDBSCAN, which is a density-based clustering algorithm. Actually, when it comes to clustering, there's no a method that is specifically designed for time series data, but we're going to see how we can apply HDBSCAN for time series data and for this particular data set. Okay, let's study together. Okay, so HDBSCAN. The intuition is that in our data space, there is a low density region and high density regions. The data points in the low density regions become noise, while the data points in the high density regions form cluster. And these clusters might have different density values, density levels, or they might have different area. Some are larger than others. And so we want to find these clusters in a hierarchical way. Okay, now we're going to go through this algorithm, how this works, but we're going to use the synthetic data set first. Okay, so these are the libraries that I'm going to use. And then with synthetic data set, I already make it. So we will have 50 samples, 50 data, and we will have 3 clusters. And then, it's going to be a 2-dimensional data. Let's run this. Oh, I forgot to start the session. Anyway, since our data set earlier has no labels because it's an unsupervised learning problem, so we're not going to use labels here. Oops, I haven't run. This data set has only 2 features, so it doesn't seem like a time series data. So if we want to stick with a theme of time series, we can think of this synthetic data set as 50 time series, and we're only visualizing the first 2 values. So for example, the x-axis represents the t0 values and the y-axis for t1. Okay, so this is our data set. This is how our data set looks like. Okay, now that we have the data, we can go through the algorithm. But first, we need to set a parameter, which is the minimum points in a cluster. We're going to set it to 5 for now. This means that to form a cluster, to be claimed as a cluster, we need 5 points at minimum. Next, we need a distance matrix. So this is a matrix to store the distance between pairs of points. And we're going to use Euclidean distance to calculate the distance between points. The distance matrix is stored in distmat, distance matrix. And then I'm going to visualize the distance matrix with a heat map. If you notice the color map, I'm using color map of tab 10, so it's not a gradient color map. I'm using this because I want to be able to fine grain the distances, like categorize the distances. So let's say that we want to have a cluster and the points in that cluster have only distance ranging from 0 to 5. That means we can have clusters that only includes the blue and orange pixels. But let's say that we increase the threshold to 10. That means we can have clusters that includes blue, orange, green, and red, and maybe some of the purple pixels. I have to admit that this might be more useful in DBSCAN. So if you're familiar with DBSCAN was developed before HDBSCAN, and DBSCAN uses the same density level for all clusters. In other words, the distances between points have to be the same. Okay, now that we have the minimum points and the distance matrix, we are actually ready for HDBSCAN. And actually, if we want to run HDBSCAN only in few lines of code, we can do this in this cell. So first we initialize the HDBSCAN class. I name it as cluster and then fit it to our data. I'm going to run this just to get the some results that I'm going to need later. And now let's study what's under the hood of HDBSCAN algorithm. So the first step in HDBSCAN is to calculating the core distance of each point. So core distance of point P is defined to be the distance between point P and the minimum points nearest neighborhood. Since we already set minimum points to be 5, that means core distance of point P, or each point in this particular dataset, as the distance between that point and the 5th nearest neighborhood. Okay, let's say that in this cell, I calculate the core distance of 2 points, point P, which is data number 16, and point Q, which is data number 20. Okay, we can visualize the core distance as circles. So here, even without looking at the annotation here, we can see that circle P is larger than circle Q, meaning that P has larger core distance than Q. And it's verified by this annotation. So we will have overlapping circles, because each data will have its own circle. Okay, and then let's move on to the next step, which is calculating the mutual reachability distance. This is a pairwise operation. So the mutual reachability distance between point P and Q is defined to be the maximum value among 3 values: the core distance of point P, the core distance of point Q, and the distance between P and Q. All the distances here are calculated using Euclidean metric. So, like in core distance, we want to get the distance between point P here and the 5th closest or 5th nearest neighborhood. We have to calculate the distance between point P and the rest of the points. And then we sort the distances and then get the 5th, well, actually, technically the 6th, because the first, like the very nearest neighborhood will be itself. So we're taking the 6th value, assuming that we're sorting it in ascending way. We're taking the 6th value, and that's going to be our core distance. And for mutual reachability distance, we will take our distance matrix again that we set here, and just take the distance between point P, which is point number 16 here, and point number 20, which is here. Okay, so yeah, somewhere in this area. Okay, visually, it will be a line going from point P to point Q. And I already made the annotations here, and it's clear that the distance between P and Q is the maximum among these 3 values. So the mutual reachability distance between point P and point Q would be 8.43. We will do that for every pair of points, and the output of that would be a graph. So each node represents the data points, and each edge represents the mutual reachability distance. So it's going to be a weighted graph. In graph theory, it will be called a weighted graph and undirected graph. So to calculate the mutual reachability distance of all pairs, I made this function. then I normalize the distance just to make it easier to visualize. But actually in the real algorithm, it's not going to be like that. So this is the real output of step number 2. As we can see, it's very hard to look at. And computationally, it's inefficient because we have so many edges to go through. Instead, we want to build a graph or a tree which reach a node only once with the least cost or the least weight. So this leads us to step number 3, which is building a minimum spanning tree. Minimum spanning tree is just like what I described earlier. It's a tree which covers a node, which reach a node only once with minimum number of edges. Or since this is a weighted graph, the minimum weight. The clusterer here is from HDBSCAN class earlier. This is one of the possible minimum spanning tree. As you can see, the farthest points is this pair because it has the highest mutual reachability distance. That means they are the farthest. Now, with this minimum spanning tree, we're ready to make a single linkage dendrogram. So this is like basically sorting the edges into a single linkage tree. So in single linkage, we are fusing 2 clusters that have the minimum intercluster distance. This is our single linkage dendrogram. When we build a single linkage dendrogram, we go from the leaves. So the bottom here is the leaves. And then we add one data point by one data point as we go further and further. From this dendrogram, we can move on to the next step, which is condensing it. The goal of condensing this dendrogram is to generate cluster candidates. Okay, let's see the output first. Oh, actually, I just remembered that I've run this code before, and I put it in a PDF file. So this is our condensed tree, and from this we can see that we have 5 cluster candidates. 1, 2, 3, 4, and 5. And the y-axis is no longer a distance scale, but lambda value. So far, I've just said density value, but never denoted. So the notation for density value is lambda. So more formally, lambda is 1 over the distance. In a dendrogram, the distance going from root to the leaves will decrease, as you can see here, from 6 to 0. But the lambda value would increase from root to leaf. In addition to cluster candidates, step number 4 also records the lambda values at which those data points enter and leave a cluster. With that being said, let's talk about what are we actually doing when we're condensing a single linkage tree. So we're moving from root to leaves, and we cut the dendrogram at several places and evaluate the clusters that are generated from those cuts. Let's say that we cut the dendrogram here first. At the distance, since this is a distance scale, let's say that the distance that we cut the dendrogram first is 5.8. We evaluate the clusters that are generated from this cut, which we have 2. The first is here. Actually, wait. Let me draw it more precisely. So this one and the big one here. Okay. And then we evaluate the clusters. If both children have minimum points leaves or more, that means this is the true split. The split at distance 5.8, or more commonly at density level of 1 over 5.8. Okay. At this density level, we have a true split, and all the data points leave the parent cluster. and enter their respective clusters. So first of all, when we got the dendrogram at all, we have the first cluster candidate, which is the single big cluster, and all the all the data points are the member of this cluster candidate. And each data point happen to have the same lambda minimum and lambda maximum. Lambda minimum is the lambda when they enter a cluster. So sometimes it's also called lambda birth. Or maybe we should name it lambda in. I don't know, I've never seen lambda in and out in a literature. But lambda minimum, lambda maximum, and then lambda birth and lambda death. So lambda maximum is also called lambda death because it's leaving. It's a lambda value when the data is leaving a cluster. Anyway, so for this cluster candidate, the very first cluster candidate, all data points happen to have the same lambda minimum and lambda max. So the lambda max would be 1 over 5.8. The lambda minimum should be 1, maybe 1 over the maximum distance. I guess this is a bit more than 6 point something. And then at density level 1 over 5.8, we have new clusters, right? Let's say that C2 on the left and C3 on the right. So the points in cluster 2 will have lambda minimum 1 over 5.8, and the same goes for cluster 3. And then we cut the dendrogram again, maybe here. This is our new cut. Let's say that we cut at 1 over 3.1. Let's say it's like that. And we evaluate the clusters again. At this cut, we still have C2, but then cluster 3 splits. Cluster 3 splits into 3 clusters. So 1 here. And then we have one single data. That's the second split. And then the third split, or the third children cluster is this. Recall that our minimum points is 5. So we have only one child that has less than minimum points leaves in the cluster. Okay, in this case, we are getting a second scenario. So the first scenario is all children have more than or equal to minimum points leaves. But the second scenario is one child, at least one child of them has less than minimum points leaves. In this case, the parent cluster still retains the cluster, but it's losing points. Okay, so cluster number 3 is losing this particular data. Consequently, this data point becomes noise. And for this data point, this particular point, let's name it maybe F, point F. So the lambda min for point F is 1 over 5.8 because that's the first time point F entering cluster number 3, right? But the lambda maximum for this point is 1 over 3.1 because this is the density level when point F leaves cluster 3. Another consequence of point F being a noise is that it's not going to be included in a condensed tree. So we see here in the condensed tree here, the length of the horizontal line, or like the width, if you will, the width of this cluster represents the total points in that cluster. So we see like in this cluster, the width are shorter and shorter as we go down. That means as we increase the density levels, more data are becoming noise. Okay, back to our dendrogram. And we keep doing that. We just keep doing that. We keep cutting down and down. We move gradually from the root to the leaves. And we also record the lambda maximum and minimum values for each data in the clusters that they are going into. So that's the output of step number 5. Now the last step is to select the clusters. From these 5 candidate clusters, which clusters are the final one? Well, I'm going to show you the result later. But to do that, we need to compute the stability of each cluster. And eventually, we want to maximize the total stability, or the stability of all clusters that are selected. So stability of a cluster, denoted as S of C, is defined to be the sum of lambda value ranges for each point in the cluster. So for all points in a cluster, okay, so for point I in a cluster, we calculate the lambda maximum I. We take the difference between lambda max and lambda min of that point, and we sum the differences. If we do this for each cluster, that means we will have stability cluster 1 and then stability of cluster 2. We will have an array of stability values. And since we have 5 cluster candidates, we will have S1 up to S5. And the clusters that we will choose are the clusters that could maximize the total stability, with one condition though. The condition is that if the child cluster has been chosen, then its parent cluster cannot be chosen. So let's go back to our condensed clusters here, condensed dendrogram. Let's say that this children cluster is chosen. Then this particular cluster candidate won't be chosen as our final cluster. This constraint is to avoid having overlapping clusters. So that's how it works. Now let's look at our result. So this is the final clusters. These 3 clusters have the biggest or the highest stability. That means if we change with changing lambda values, these clusters are quite robust. And visually, we can think of choosing clusters that has the biggest area. We can see that these 3 clusters are bigger than this one or this one. Okay, so that's it about HDBSCAN. If you want to know more about it, you can refer to these papers. Unfortunately, I cannot get the access to the original paper, but these papers and this website actually explain HDBSCAN really well. And so what I explained just now was sort of the summary from these 3 references. Furthermore, if you want to know more about HDBSCAN from different perspectives, such as from statistics and topology, you can read this paper. Okay, so now let's apply this to our dataset that we saw earlier. Okay, now here we are in another Kaggle notebook. This is to apply our knowledge about HDBSCAN to this sales data. Okay, first let's start our session. So the data set, as I showed you earlier, it's from UCI Machine Learning Repository. It has its own library, so we don't have to download the data manually, but instead we can import in Python. So we install the library, which is UCIML repo, and then import the library and just load it. we're going to apply HDBSCAN using sklearn. And if we saw earlier in the theory section, we apply HDBSCAN using HDBSCAN library. The same library is used in sklearn. So, but notice that I install another sklearn. Well, actually not as another, it's just I upgrade my sklearn because we have to use the latest version of sklearn. Otherwise, we will use version number 1.2 if I remember correctly. 1.5. Oh yeah, 1.5 is the latest, and if we don't upgrade, we will get version 1.3. In sklearn version 1.3, HDBSCAN is not there yet. Okay, now that we've imported all the libraries we need, we just need to load the data. This code snippet is copied from the data web page. So if we click import in Python button, we will get this. I'm going to close this tab now. The data itself is stored in data features, and we're not only getting the data, but also the metadata and some other descriptions like the list of variables. Okay, let's look at X now. X is the raw data, and so originally the raw data is not storing only the raw quantity sales, but also the normalized ones. But we're not going to use it. So yeah, we just take the first 52 columns and save it to TF. And this is the data that we're working with for the rest of the video. Okay, a simple ETA, visualization of the time series. These are all the time series, okay, from week 0 to week 51. And yeah, we can see there's a separation here and a cross here. So I don't know, I expect to see 3 clusters at least. Hi, in addition to this, I added a new visualization because I think this will be useful later. And that visualization is like in the theory section, which is plotting the data based on the value, the first and the second value from all time series. If we see this, we might think that they are positively correlated, and yeah, it's true. But this is not the point of this video, so yeah, I'm not going to talk about it. So the x-axis is the first value of all time series of all sales in the first week, while the y-axis represents the second value, or T1, of all sales. And then the next cell, I'm calculating the distances between pairs of points and visualize it as heat map. Now we can see that there's a bunch or like an area of blue boxes now. Again, the distance formula that is used here is Euclidean distance. Okay, I'm going to show you how the heat map will look like and the clusters look like if we're using TTW as our distance metric. Okay, but now let's use clustering with Euclidean distance. Euclidean distance is the default value of HDBSCAN. So I'm just using all the default values here. We initialize the class by HDBSCAN and then fit it to DF. We can see the default values here. So the minimum cluster size is 5. This is the same as min points earlier. And then metric Euclidean. If we set the metric to be pre-computed, that means we have to fit a distance matrix instead of raw data. Again, HDBSCAN can be used with any distance matrix. Here, cluster selection method parameter. The default is EOM of or excess of mass. This is the method that we have seen in the theory section. The alternative is leaf. So we just take the leaves as clusters. But excess of mass is the method that is recommended. It's recommended by the inventor of HDBSCAN. Okay, so let's run this out. It's quite fast. And we can see if we use HDBSCAN by all the default values, we will find 1, 2, 3, 4. We will find 4 clusters. The clusters that are, the data points that are labeled as -1 means that it's a noise. So I guess the majority of the data fall in the cluster number 3. It accounts for 60% of the whole data. Now let's visualize the time series in each cluster. Okay, so there it is. Yeah, well, by default, we also put the legend. And maybe the legend is useful if you want to know which product is in which cluster. But I know that I'm also aware that in cluster label 3 there will be too many, like, oh my god, the list is so long. Yeah, so let's change that to false. Okay, like this. So we can see that each cluster has similar trends, similar products. Perhaps cluster 2 and cluster 3 are the most similar, but we can see that in cluster 2 there's no zero. There's no product with 0 sales, whereas in cluster 3 perhaps we can think of products in cluster 3 as like the least bought items. And the products in the noise cluster, in cluster label 1, we can see that the sales in this cluster is the highest. And if you see here, the print thing here, we have 155 products as noise that don't belong to any other clusters. And that's around 19% of the whole items sold in that supermarket. By using Euclidean distances, we are calculating the distance between sequences by the magnitude only. And so we can see that the magnitudes of each sequence in the cluster are quite similar. But if we want to see it based on the shape or based on the derivative of the sequence, it's quite interesting to see cluster label 0 and label 1, because we can see that almost all products in cluster label 0 have decreasing in sales at the end of the year, while for products in cluster label 1 have increasing at the end of the year. They have 2 groups among these clusters, the first half and the second half of the year. And it seems like for cluster label 0 products, the sales of them in the second half is lower than the sales of them in the first half, while in cluster label 1, the sales trend is roughly the same, except for peaks here at June perhaps, and at the end of the year. Okay, so that is the HDBSCAN cluster results by using Euclidean, using all the default values. Now let's try a different clustering by using TTW as our distance metric. So we have to calculate our distance matrix again, sorry. And I'm using TS Learn Library for this. And the DTW version that I'm using is the basic one, so no constraint, no variation whatsoever. It's the very first DTW. And then we will see how the distance matrix differs. Okay, we save the distance matrix with DTW as distances DTW. And now let's compare the distance matrix calculated with TTW and calculated with Euclidean. Well, we can see that there's more blue pixels here, because on the left we see more orange in the middle of blue pixel. And I guess this is not really surprising. Recall that DTW aligns the sequences better, in my opinion, rather because they also consider the value of the sequence rather than just a line based on the time index, like in Euclidean. Okay, but we'll see how the cluster will be different. Oh, sorry, just realized here. HDBSCAN, since we are using a distance matrix, so we should use metric pre-computed. So we have the distance matrix already, which is distances TTW, and so yeah, we need to use metric pre-computed and then fit the distances DTW to our HDBSCAN class. And then let's see the clusters result. Wow, we have from 0 to 20, we have 21 clusters and 1 noise. But we can see that each cluster has much fewer members, like only 5, 6, 23 is the most, and then most of them are considered as noise here. Okay, so here are the clustering results. For cluster 0 and cluster the noise, well, at least for cluster label 0, it's pretty much the same as in cluster label 0 using Euclidean here. But for others, it's very different. But we can see that most of them, well, from cluster label 5 to the end, to label 20, they are very minimum. Like perhaps they are the least bought items in the supermarket or among 811 products. Okay, if we want to compare the results from the clustering results by Euclidean and by TTW, I guess the biggest difference is in cluster label 3 of Euclidean distance metric. So using Euclidean metric, we see that the majority of the products are in cluster 3. And it seems like those products are broken down into many little clusters if we use TTW metric. Yeah, judging because of the magnitude from these plots, the subplots of cluster label 5 to cluster label 20. And also notice that if we combine cluster 2, 3, and 4 from TTW metric, I think we'll get cluster label 2 in Euclidean metric. So it seems that cluster TTW breaks down the products in cluster results from Euclidean metric. And to confirm that, I'm using scatter plot that we used earlier. So earlier, in the scatter plot earlier here, we just use brown color, all in brown color. But after cluster it with Euclidean metric, this is our clusters. The blue dots are noise. And we can see, yeah, those blue dots are here interfering with the green cluster. The point is the lower left corner here, okay, notice that. I'm going to show you the same plot but using TTW metric now. So here it is. You see the lower left here has many different colors now. The point is that the gold area has broken down into many different colors, meaning that the least bought items are in cluster label 3 with Euclidean metric is now broken down into many clusters. If you ask me which clustering is better, it's quite hard to decide. it really depends on our application. Because my question in the very beginning of the video is only about finding the clusters using HDBSCAN. So yeah, I cannot decide based on that goal only. But yeah, it depends on the goal eventually. So if we want to have greater detail on how these products are similar, then perhaps the clusters detected by a TTW metric is better. But otherwise, maybe the default is doing a better job. So yeah, given these clusters, we might want to do different things. We might want to discontinue sales for several clusters, or perhaps we want to change the marketing plan for another cluster. And yeah, so that's it for today. We've studied what is HDBSCAN and we have applied this to our sales data. Thank you so much for watching. The code will be uploaded in my Google profile and also GitHub. If you enjoy watching this video, please consider subscribing to my channel, Timely Time Series. Okay, I'll see you next time. Bye bye.